Hi, my name is Pramod. I'm from the CoinOp collection, and basically today I'm going to go over some basic Verilog stuff. So in the next few days, we're going to be releasing some code bases, and so in order to understand them, I it would be preferred that you have a basic working knowledge of Verilog, and so I thought I'd go over quickly. Some basics and how things work in the language, so you're better able to understand what's going on. This is not intended to be a full replacement for a Verilog course. However, basically, these are the essential things that I think are the common patterns that I use normally in the language, just to kind of give you a functional working knowledge. Okay, um, so I've put together some basic examples here of things that I think would illustrate what the language is about. Okay, so let's start with variable assignments, right? So like basically, there are wires and registers, right? So wires are always continuous all the time, right? These are things that will always update in real time. They're not there. There's no conditions involved for them to update. It's always continuous all the time. It's always constantly evaluating, right? And registers get updated at specific points in time or specific events. There are cases also where registers can become continuous as well, in specific types of cases, like if you have a temporary variable type of case, it would become continuous instead of registered. If you use it in the registered case, like in a procedural or non-continuous fashion, basically it gets assigned, and then the value reflects on the next clock edge. Okay, so concerning concerning this, I'm talking about using the clock condition, like a rising edge to assign things to registers. Wires are assigned outside of those those always blocks or those clocked edge blocks, and are always evaluating. Okay, like this. This is a continuous assignment. Okay. Now, let's talk. So that's the basics. You have regs and you have wires. Registers are done on some sort of clock edge or some sort of. There's an always star block, they call it, where a register can be assigned stuff and be continuous, like an equivalent of a wire. Only you have like procedural code to back it up. There are cases of that. So, for example, if you have, well, first of all, I'm going to show you the regular case, right? So every time this clock hits an edge, right, which is every 10.417, not 10.417, every 20.834 nanoseconds, because this is the half period, right? So like basically every time from rising edge to rising edge, it's going to be 20.834, right? So every time that happens, you can say counter equals counter plus 1, right? So every time a clock edge happens, this counter will increment and the previous value will be retained. However, this wire value, which is wire plus counter plus 1, this is always evaluating, right? So once this counter takes effect, right, which is in the next clock cycle, not this one, but the next one after this, this is going to be whatever 0. Well, if it's 0, it'll become 1. This will become 2. Okay, so that's how that works. And I mentioned about the always star blocks, right, where a reg can become a continuous type of thing. Actually, The best use case I can think of for this type of thing is basically your address bus. So if you have a CPU and you're trying to segment your address bus, usually we use the always star block. So if you have like ACS, BCS, or CCS, right? What you can do is ACS equals, and not this equals, right? Because that's a procedural assignment, right? That'll happen in the next block, right? A next clock edge that'll take effect, but rather uh, a continuous assignment right here. So basically, if you have ACS equals, like let's say you had a, right? Right? Like, let's say you had your address hooked up to your to your CPU coming out, right? So A1514 equals to B11, for example, and then you have BCS like that, like something like this, and then you can use these selects to drive your bus logic. So that's where I use that normally most of the time, is that that's use case, and then this I use every day, all the time, every time, right? Because this is very important. These structures are very important. Okay. Right, and these are treated as continuous. So as soon as this happens, this is going to take effect. Now, if it stops happening, then something else will take effect, or nothing will happen. None of these will be activated. Right. So this is all continuous all the time because it's an always star, but it's also declared as a reg. Right. So what you can do is you can apply if statements. So let's say if some condition is happening, you can choose not to evaluate this. But then what happens is you have to set some default value for this at the top, right? Because if you're gonna gate these by something, like let's say you're like I don't wanna do any CS detection. I don't want to do any address bus detection if the address is not valid. For example, like on a 6809, it's the VMA, right? If it's the 68K, then it's the valid peripheral address, and or other sorts of signals that tell you like, oh yeah, this is a valid memory address that's coming out of the CPU. Then don't do it. Everything else is zero. So you have to set a default. Otherwise, what happens is in synthesis that'll become an inferred latch. Okay. All right. Now, number two, let's go over scoped variables and temporary assignments, right? So in Verilog, it is possible that you can do something like this. Okay, and you can do like well, they don't have to be integers, but like if you do like reg of 70, the width of the signal, by the way, A, B, C, right? You can do A equals 1, B equals 2, and then C equals A plus B, right? It's possible to do that. So you can treat A and B as temporary variables to do some things. Like let's say you have a complex calculation and you don't want to like inline it all here. You can actually have temporary variables, and you can do it like this. You can do a combinational assignment, which will take effect immediately, right? So this after this line goes, this A will be 1, and after this line goes, B will be 2. A plus B will not take effect immediately. It'll take effect in the next clock cycle after this one. It'll be queued for change. Okay. Now, one more thing you can do is create scoped variables, right? Or local variables, right? So pos edge clock. If you name a block, right, temp1, for example, you can do something like this. Temp1. Actually, let's not name the same thing. temp2, and then you can do temp2, like something like that, right? Yeah, so you can absolutely do that. You can have variables declared inside of the blocks only if you name the block, right? So this is called a name of the block, okay? If you do the colon in that, it's a name. Okay, so that's how the mechanics of variable assignments work in a nutshell, and that's how they're used. Now, the next thing I do all the time is rising and falling edge detection, and the reason why I do this is because often at times um, you need to take action on something uh, when it first goes high or goes low, right? So all these types of signals in Verilog and on the FPGA and all that stuff, they're all like continuous signals, right? They have some of them have like rising and falling edges. Some of them stay constant for a while, then go down and go up like a pulse. They're all different types of waveforms, right? So like a lot of the time what I'm doing is I want to detect the I want to take action on something when the rising edge of it happens or the falling edge of it happens. However, I do not want to do that while it's low, right? Because it's going to be low for quite some time, or it's going to be high for quite some time, right? I don't want to take action every single time it's in that state. I want to take action just a one-time deal when it goes high or when it goes low, and that's called rising and falling edge detection. It's very important. And basically, what that involves is that pattern involves a you have to store the last value of that particular variable. Or in this case, it's just clock, just as an example. But this is clock. This prev clock will be the value of clock in the last cycle, right? Because remember, when you do these types of assignments, they take effect one clock cycle later, right? So this is already the value in the last cycle, right? So it's one cycle delayed. And so I can compare what the value was before and the value is now, right? So if the previous was high, right, and the current is low, then it would be a falling edge. If the current is high and it goes low, I'm sorry, if the previous is low and it goes high, then it's a rising edge, right? So this is actually backwards. So like if it's a rising edge, no, I'm sorry, this is good. Yeah. So yeah, on clock. Yeah. So if the previous clock was high and the current is um low, then it's a falling edge. If the previous was low and it's high now, then it's a rising edge, right? And so I can use that to detect something. So I can use this falling edge or rising edge signal to say, hey, do something now, right? Or trigger something, or do some start a state machine, do something, right? Do something, and then just don't do it again, right? Until the next time. Vertical blank, horizontal blank. These are types of things that have defined waveforms. Like they stay high for the majority of the time, and then they immediately go low, like thereafter. So like basically, you want to detect the moment they're low, do something, and then just continue doing it until the next time it goes low. And you only want to take action when it goes from high to low, right? So that's your edge detection. Okay, let's talk now about pipelining. Pipelining is a very important concept. It's used in a lot of different places. Like more frequently, it's used in synchronization types of things, right? Or it's used as a way to process streams of data. I've used this type of pattern in streaming data. Like for example, if you have a use case where data is streaming out to you, like SDRAM, for example, right? SDRAM will, like if you're doing like burst in an SDRAM, that's basically going to stream data out to you one clock cycle after the other, right? And you have to, like, let's say you want to take that data and you want to process it in stages, right? But you don't want to block new data from coming in, right? Because like data is continuously flowing. You don't want to stop that flow, but what you want to do is kind of move it along an assembly line of sorts, right? And so that's what this does, right? In a simple example. So the first, imagine counter being like a thing that increments every clock cycle, right? So on T0, right, counter is 0, right? So 0, then um, this will get assigned immediately too. So this is, let's say, 0. This is also 0, right? Everything's 0 at the start, right? And then when counter becomes 1, this is a 0, right? This becomes 1, and this is still 0 again, right? Because it hasn't reached stage 3 yet. So that basically you have a point where, like, okay, now this is counter equals 1. Now this is 2, then, like, and so on and so forth. So the counter is always changing, and it's moving through the stages one at a time, because all of these, because it's a synchronized assignment, all of these are delayed one cycle, right? Because they get queued ahead. So basically, it's like an assembly line of sorts. Counter flows into here, then this flows into here, then this flows into here. Like it's and meanwhile, counter is changing every single time something moves from A to B. Like every time this moves from this to this is already a different one. Now it's queued a different one here. Like so, it's kind of moving it along an assembly line of sorts. And you can do a lot of different things with that. Most of the time, I use it for synchronization. I don't usually use this pattern all that much. I use it sometimes, like when I have streaming data involved, but I generally don't use this pattern a whole lot because I think it creates confusion. Normally, most of the time, I will opt for using a state machine if it's something that I need to do that is a step-by-step process. I'll usually use a state machine for that because that's just more clear. It's very clear what the intent is, and it's very clear what the steps are. Okay, so with that, let's go to the state machine. So state machine is extremely important. Generally, it is a good idea to define local params for your states and name them appropriately in at the start of the state machine, right? It's good, and you need uh, there's multiple ways to do a state machine. This is the traditional way, I would say, where you have a state and you have a next state. So basically, your state transition logic is apart from your action logic, right? So basically, in this short example, what happens is state transitions at clock edges, right? Because that's a value that's not a continuous thing. That's something that has to be retained for one or more clock cycles, right? And then this is your state transition logic, right? This is just the transition logic. And sometimes it's broken into two parts. There's your actions of what you need to do in each of the states, and then there's the transition logic of moving from point A to point B. And sometimes it's useful to have them in separate parts. I generally don't do that. I generally put them all in the same part. I'll show you that in a second. But like, I generally do not do state machines like this. Sometimes it's useful. Uh, sometimes yeah, sometimes it's definitely useful, but I generally just don't do it that way most of the time. Sometimes I do, but not all the time. You don't have to do it one way or the other. It doesn't really make a difference. It depends on what you want to do. um, and this is displaying the state transition. So obviously there's a counter, and counter is always incrementing. So like if you have it in separate parts, it makes it a little bit more complex. But from a timing perspective, it might actually be better because it might be quicker, depending on what you're gonna do. But still, the concept of a state machine is basically you have step 1 has to be done before step 2, before step 3, before step 4, and so on and so forth, right? So like the very basis of it is that. It's just that I guess it makes it more hardware oriented if you do it separately, because in real hardware, this would definitely, I mean, if you didn't have an FPGA, this would definitely be separate things, separate circuits, and all that stuff. But I don't usually do it this way. But anyway, this is how that works. So you define what your states are. You have something that sets the next state, and then you have state transition logic in a continuous way. It's always going to be continuous in this one. And then you have your actions, right? Your actions are basically going to display the messages in this case in the simulation bench when you do them. Okay, there's another way to do a state machine, which is an automatically advancing state machine. So that is like this. State 2, for example. Let's make that 3 states, right? And then you do always, so clocked, synchronous reset. All right. All right, and then you do your case state 2, right? And then what you can do is state 2 plus 1, right? That's your automatically advancing one. And then you do 0, I don't know, assign A equals 1. D equals 3 or something. I don't know, something weird. Yeah, so this is an automatically advancing state machine. It's kind of like, yeah, it is a state machine, but it's kind of similar to the pipeline example, where you're constantly like changing the value of one thing, and since this is based on the current cycle and it goes to the previous, so your next cycle will basically reflect the previous one. You're just taking action on whatever it is. And in Verilog, you define you find your bit widths for your variables, and they can roll over. So if I'm at 3, right, which is the maximum number a 2-bit thing can store, right? If I say plus 1, right, what's going to happen is that's going to become 0, right, because it rolls over and it can't accommodate that third bit. So it truncates it and it becomes 0, right? So it's continuously looping over and over again. So that's how you do that. And that's an automatically advancing state machine. And in any one of these states, like let's say I wanted to automatically advance, and then in some exceptional cases, like let's say here I say, oh, okay, so if B is 10 or something, right? Then do this over, or go to skip to 3 or skip to 1. It doesn't break this logic. It's still automatically advancing. It's just that you're overriding it in here. So if you have two clocked assignments, or non-blocking assignments, they call it, one after the other, the second one will override the first, right? So you'll not break this automatically advancing part of it, but you'll just kind of do it that way. And yeah, this is technically a state machine, but it's like, I would say it's more of a pipelining example than anything. Okay, so there's that. And so yeah, we covered that type of state machine. We covered pipelining, like formal pipelining where you have streaming data. We covered scoped variables, right? I told you if you name it like this, you will get to use instantiated variables in here in the actual block. That's a local variable, a scoped one. You can't access this temp2 outside of this. And then you have your counters, basic registers and clocks and that sort of thing. One more thing that's very useful, that I use a lot of times. I mean, I don't use it super often. I should is called a task. And it's exactly as this example says it is. So basically, a task will do something. A task is not like a function. So a function basically is a combinational thing, and you can do function too. Like so, function. Yeah, so like add, right? So basically, this is basically there's a function and a task are two different things. So functions I use extremely often, right? For calculations and things that need to be done immediately, right? And it's a continuous combinational thing, right? A function. Um, Task is basically code that you can use it for continuous stuff, but you can also use it for clocked stuff too. But basically, from a synthesis perspective, task will just inject whatever code this ends up being in the body into wherever you put it, right? So it's good because like basically if you want to create repetitive logic across multiple sections of your clocked assignment blocks or whatever it is, you can use the task to effectively do that. So you don't have to keep writing the same thing over and over again. You can just have one task and have that code repeat like multiple times because that's literally all it does from a synthesis perspective. It does more things in from a simulation perspective, but from a synthesis perspective, basically all it does is take your current code in here and just copy them into wherever you put it. Okay, and it makes life easier because you can just write things one time and just go with that. Okay, so that's that. That's your continuous assignments. Let me see if I'm missing anything. I don't think I'm missing anything basic. Mm, yeah, so those are really the basics. I mean, that's as basic as you get from a pattern perspective. I use all these patterns all the time. These are the essential building blocks of Verilog. And next time, what I'll do is I'll go over some more advanced things that I use. But basically, it boils down to the essentials here. And one more thing I wanted to say is, during this uh, during this brief tutorial, I use GitHub Copilot, right? And so I have to say like if you're going on the journey of like kind of learning Verilog and learning FPGA stuff, it's absolutely okay to use AI tools. It's absolutely okay. However, um, you should really understand what it is you're doing before you use those tools because they can easily mess you up, right? If you know what you're doing and you have a good grounding in the subject matter and you want to use AI to streamline your workflow and make life easier from a code generation or idea generation perspective, I absolutely support that. I think that's a good use case for AI. I think a bad use case for AI is if you try to do something that is way outside of your league and you have no idea what you're doing at all, and you just start going into AI, generating prompts for things, and you start like randomly doing things that you have no business doing, and like you have no idea what the hell's going on. And I just think that's just gonna result in like just wasted time, and it actually might screw up your learning. So what I suggest is get a good grounding in the subject matter itself first. You can use AI to generate things for you, but always like try them out and experiment with them, see what the effects are of doing them. And then you can continue to use AI more and more to generate things that you want to do or make your life easier. I think that's probably the best idea. AI can do a lot of things, but only if you know what you're doing. If you don't know what you're doing and you're just trying to do random things that you have no business doing, I think it's going to turn into a disaster, and basically like you'll end up in a hole that you can't dig yourself out of. Okay, so that's my statement on use of AI. Totally okay as long as you understand the basics and you know what you're doing. If you don't know what you're doing, stay away from it. That's what I would say. Okay. Let me see. Yes, so this covers like the basics, the basic Verilog stuff. In the next video, what I'll do is I'll show you some tools that I use and how I use them in my workflow, and then we'll go through some more stuff. Okay, so I'll see you in the next one.